Today we are going to learn about backpropagation demystified, the core of neural learning. You'll understand the mechanics of backpropagation, the role of gradients, and how to optimize neural networks. Gain skills in calculating partial derivatives and using the chain rule effectively. Welcome to our video on backpropagation demystified, the core of neural learning. In this brief introduction, we'll explore what backpropagation and why it's a cornerstone in the world of neural networks. Backpropagation is a method used to calculate the gradient of the loss function with respect to all the weights in the network. It's essential for optimizing neural networks, allowing them to learn from data efficiently. This process helps in adjusting the weights in the network to minimize error, making it a critical tool for anyone working with AI and machine learning. Gradients play a pivotal role in the learning process of neural networks. They are essentially derivatives that measure how much the output of a function changes as its inputs change. In neural networks, gradients are used to minimize the error by adjusting the weights. The process of adjusting weights is known as gradient descent, a fundamental optimization algorithm. By following the direction of the negative gradient, we can find the minimum of a function, which in our case is the error function. This is analogous to climbing down a hill where the slope indicates the path of steepest descent. Understanding gradients is crucial as they guide how weights are updated, influencing the learning dynamics of the network. Partial derivatives are a fundamental concept in calculus, and they are indispensable in neural networks for calculating how a change in one variable affects the error, holding other variables constant. This concept is crucial for understanding how each weight in a network contributes to the overall error. By calculating partial derivatives, we can determine the precise direction and magnitude of change needed for each weight to minimize error. This process is part of the chain rule in calculus, which we'll discuss later. Mastery of partial derivatives allows us to update weights effectively, ensuring our neural network learns and improves its accuracy over time. The chain rule is a powerful mathematical tool used in the backpropagation process to compute the derivative of composite functions. In the context of neural networks, it allows us to calculate the gradient of the loss function with respect to each weight by breaking it down into simpler parts. Each layer of the network can be seen as a function of the previous layer, forming a chain of functions. The chain rule helps in propagating the gradient backward through the network, hence the name backpropagation. By applying the chain rule, we can efficiently compute the partial derivatives needed to update each weight, enabling the network to learn from complex datasets. Let's walk through backpropagation with a simple neural network example. First, we perform a forward pass where we calculate the outputs of the network given an input. This involves passing the input through each layer of the network, applying the weights and activation functions. Once we have the output, we compute the error by comparing it to the expected output. The backward pass is where backpropagation truly begins. We calculate the gradients of the error with respect to each weight by applying the chain rule, starting from the output layer and moving backward through the network. Each weight is then updated in the direction of the negative gradient to minimize the error. This process is repeated iteratively until the network learns to produce accurate outputs. Backpropagation, while powerful, is not without its challenges. One common issue is the vanishing gradient problem, where gradients become too small to effectively update weights, particularly in deep networks. This can lead to slow learning or the network getting stuck. Conversely, the exploding gradient problem occurs when gradients become excessively large, causing instability in the learning process. Overfitting is another risk, where the network learns the training data too well, failing to generalize to new data. Choosing an appropriate learning rate is crucial. Too high can cause the network to diverge, while too low can slow down learning. Debugging these issues requires a keen understanding of the network and often involves trial and error. When faced with backpropagation challenges, several practical techniques can help. Monitoring gradients during training can provide insights into whether they are vanishing or exploding. Adjusting the learning rate dynamically or using adaptive learning rate methods can mitigate these issues. Regularization techniques like dropout can help prevent overfitting by randomly ignoring neurons during training, encouraging the network to learn more robust features. Simplifying the network architecture by reducing the number of layers or nodes can also help if the model is too complex. Gradient clipping, which involves capping the gradients at a certain threshold, can prevent exploding gradients and stabilize training. Backpropagation is the driving force behind many real-world AI applications. In image recognition, it enables deep learning models to identify and classify objects within images accurately. Natural language processing benefits from backpropagation as it allows models to learn complex language patterns, improving tasks like translation and sentiment analysis. Autonomous vehicles rely on neural networks trained with backpropagation to interpret sensory data and make driving decisions. Recommendation systems use backpropagation to learn user preferences and suggest relevant products or content. In predictive analytics, backpropagation helps models to forecast trends and behaviors by learning from historical data. These applications demonstrate the versatility and power of backpropagation in advancing AI technology. In conclusion, we've demystified backpropagation, revealing its critical role in the world of neural networks and AI. By understanding the mechanics of backpropagation, including gradients, partial derivatives, and the chain rule, you are now equipped to optimize neural networks effectively. We've discussed common challenges and provided practical tips to overcome them. As AI continues to evolve, the principles of backpropagation will remain foundational, driving innovations in how machines learn and perform complex tasks. Thank you for joining us on this journey through the core of neural learning.